All right. I will begin with a word of prayer. Once I get up here. Heavenly Father, we thank you for this day again. I thank you for the students in this class and this time we have to study your creation. Lord, help us to use this time wisely. Lord, in the name of my prayer, Lord Jesus. Amen. So, cool. Let us begin. So, I want to show you guys today yet another application of the contraction mapping principle. And our focus is primarily in differential equations. So let's see how that goes. So the first thing I need to do is kind of tell you the problem we're trying to solve, which is a problem you probably have seen before, but I don't think you saw the proof of the theorem we're about to show. So let me just start us out with the problem here. And so this is my section 1.6, my current theory of differential equations. Of course, we're primarily focused on ordinary differential equations, but so here's the problem we're interested in. And I'm going to write it slightly different. dy dx equals to f of x comma y of x. All right, and y of x naught equals to y naught. So we're trying to solve this differential equation, right? Or at least we want to explain how to understand solutions to this differential equation. Like we'd like to prove that solutions exist, you know, and unique solutions exist. So if we could somehow reformulate this, you know, in terms of an operator, then we'd make some progress here. So what I'm going to do is just integrate both sides. All right. So like the integral, let's say from, well, first of all, I'm going to change the variable. So this is dy dt equals to f of, oops, my bad, t comma y of t, right? So I just changed from x to t. And then I'm going to integrate this thing from, say, x naught to x over dt, and integrate this from, say, x naught to x over dt, right? And if I do that, on the one side, I get y of x, right, minus y of x naught. On the other side, I have this integral, all right? So then, well, I want y of x naught equal to y naught, right? I want that specific value for when we plug in x naught. So I can rewrite this as y of x is equal to y sub naught plus the integral from x naught to x, right? F of t y of t dt. All right? So I've now shown you that if y is a solution to the stated differential equation, right? Then what? This implies that, right? So this is the integral form of the differential equation. Right? So which of you have had differential equations? Two. Okay, so Preston, you're at a disadvantage. Jack, you've forgotten it all. I'm just joking. You know it all because you just took the subject GRE and it mattered there, didn't it?
It definitely did.
Yeah, it did. It probably mattered. I would just, so question, the current, I know you're not allowed to talk about it, but supposing you were allowed to talk about it, like all the Chinese are doing in, you know, open message boards in Chinese that we can't read. I assure you it's happening. But
Supposing we're not recording.
of course. What would you say is a bigger topic? Differential equations or complex?
Those two, there were neither of them were a lot of questions.
Neither were, so it's kind of
It was definitely.
even Stevens. I'm querying the concentration of differential equations versus complex on the latest subject GRE test.
I think on mine I had a few more complex,
A few more complex?
but they were both, like both of them didn't have many.
Hmm.
It was a lot of.
Jack just took it.
Yeah, a lot of calculus, a lot of calc 3.
A lot of yeah, Calc 3. Yeah, I remember that. So if we have this differential equation, we get this integral equation, right? How about the other way? Is it also true that this goes back up to here? Well, I mean, check it out, right? What's y of x naught? It's y naught plus the integral from x naught to x naught. Well, that's easy, right? I can do that integral, no matter what f is, you know? So this is equal to y naught, right? Check. So it solves the initial condition. And what if we differentiate this? What's dy dx? How's that go? Well, this is a constant, so that's 0. And then by the fundamental theorem of calculus part 1, we have what? F of x comma y of x, right? So what I'm showing you is that the given initial value problem and this integral equation are equivalent. They have the same solution set. If I have a solution to one, I've got a solution to the other, and vice versa. Do you guys agree? So let me also point out that we can define a linear operator from the integral equation. Like so. We go t of y equals to ty as a function of x, all right, is equal to y naught plus the integral from x naught to x, f of t, comma, y of t, dt. All right. Now, I don't believe I can say that I don't know if that's a linear operator, right? In fact, it probably won't be for many examples, but it is nevertheless an operator, right? I put in a function, I get out a function, right? And if I knew that, for example, if I knew f was continuous, right? If I put in a continuous function, I'll get out a continuous function because the integral of a continuous function is continuous, right? And notice then, what would it mean if we had a fixed point of this operator? What would t of y equals to y mean?
Do you mean that y is constant?
No, I do not. So if you want me to be more blargy about it, I mean this is equal to that for all x in the context we're working. Y is a function.
I'm thinking of something that reminds me of a letter.
Something that reminds you of a letter. Well, while you're doing that, I'm going to hit the button. Let's see here. Man, Jordan gave me a great idea for a new problem, my differential equations test. I gotta go back and I gotta change the test. I'm gonna tell you what, it's gonna be great.
Nobody's gonna.
What's that? I know, it's awesome. Well, he said something to me in complex that made me think of a new problem in differential equations that I gotta test tomorrow. I'm giving. I gotta roll it out. It's not the strongest section of differential equations either, so it's going to crush them.
I know some people in class.
But it's going to be funny. I'm just kidding. They'll be fine. It is differential equations after all. And as you guys know, differential equations are easy.
I've never done anything with any at all ever.
Oh, yeah? Oh, yeah.
Just getting your sum right there.
Yeah.
Yeah.
So the answer to the question I was posing a second ago is that t of y equal to y means that it solves the integral equation. Look at it. If you put t of y equal to y, that means that when you plug y into the integral equation, it works. So finding a fixed point for that operator is solving the differential equation. How do we find fixed points?
Contraction mark.
Contraction maps, that's right. So if we could show that this t is a contraction map in a particular context, we'd be in good condition, wouldn't we? And that is what we're going to do. So let me get out here. But I wanted to at least write that part out by hand because I wanted to slow down enough so you guys, I want to make sure you understood that basic point there, because really that's the thing that guides everything else here for a while. So do you guys remember, for those of you who've taken differential equations, do you remember the theory? The well, not yet. Let me hold off that question. So a fixed point then is a solution to the differential equation. How do you find a fixed point? Well, you set up an iteration, right? We'll start with y sub 0 equal to the given, y sub 0, just the constant function. That's our starting iterate. Then we feed that into the operator t, and that will give us y1, and then generally we'll take the nth one and it will define the n plus 1th one by integrating the differential equation, basically. So you're just integrating over and over and over again in this way. So here's an example. This is called the Picard iteration in honor of, Picard. So, yeah. Although if you read Nagel, Saff, and Snyder, and I will post a PDF of the chapter 13, which I'm working off of, they have a little bit of the prehistory. Like, it's not just, other people other than Picard did this, but it was like papers by Picard in like, I think 1896-ish or something like that, or 1886, somewhere in the late 19th century, where this got its name, and he sort of got people's attention about how to do this. But other mathematicians had done it 50 years before him. But they hadn't promoted it as a method or been quite so,
Stigler's law of quantity that says everything's named after the wrong person.
What's it called?
Stigler's law of quantity.
Stigler's law of
Eponymity.
eponymity. Ah.
Apparently Stigler's not the first person to say that.
Stigler's not the first person to say that. Very nice, very nice. Oh man. Every semester I should take part of the course to watch myself teaching something in the previous semester, and then in the next semester I should make a point of watching that video. And then in the next semester I should make a point of watching that video, and I should just keep doing this. After about 10 years, this would be awesome. I need to start sometime soon. I'll get around to it.
Are you trying to write a fixed point in the videos or something?
Ooh, yeah. What's the fixed point of the videos? So, all right. I digress. But so here's the differential equation: dy dx equals to 2y, right? And so following Picard's iteration, Pickard. What's wrong with me? Y of 0 is 1, so I put 1 here. Integrate from 0, my x naught is 0, so 0 to x, this, which gives you that, and then do it again, we get that, do it again, you get that. And on the flip side, of course, we can solve this thing by separation of variables, and we get, a constant times e to the 2x, and if you look at the power series expansion of this guy, well, that's what we're producing, right? And I don't believe for a second this is what usually happens with the Picard iteration, because of my experience with our other iteration last time. Like, I think this is a very fortunate example that works out very nice. I fully expect that usually the iteration doesn't have like a nice tight correspondence with a power series expansion of the exact solution or something. Like this is fortunate. But it's also from Nagel, Saff, and Snyder, so I thought I'd steal it. All right, moving on. We need to settle some analysis. This is, after all, the advanced analysis course, so let me make good on that. First of all, and we've talked about this before, I think, but we want to talk about uniform convergence. So the set of continuous functions on a closed interval, we're going to define the max norm for the norm, and that exists because we're talking about continuous functions on a closed interval, right? Extreme value theorem. And so this exists. Whatever it is, that's the norm, the length of the function. And you can say a sequence of functions converges uniformly if the limit as n goes to infinity of the max norm of the difference of the sequence and the function is 0. So likewise, a sequence of functions is pointwise convergent if you have this, right? So what's interesting then is there's another way to calculate uniform convergence in terms of what's called a worst case estimator. If we have a sequence of functions which uniformly converges to y, then for every epsilon greater than 0, there exists an n for which n greater than n implies that the absolute value of yn minus x minus y of x is less than epsilon for all x in the closed interval, right? So given that condition, we have that the norm of the difference is, well, it's equal to the max norm of the absolute value of the difference, right? But this is less than the maximum of course the maximum of epsilon is just epsilon. It's dumb, but I just, I like to think about things in terms of formulas rather than logic because, I'm kind of 19th century sometimes. But anyway, so that's less than epsilon, which goes to show you that, So uniform convergence in the usual sense implies, well, let me get to the point here. Hopefully I haven't. Well, what I'm trying to say is this definition of uniform convergence I just gave in the green is not the definition of uniform convergence that we gave previously in here, right? But my point to you is that if you have this, then you get the usual uniform convergence, namely that, we can make, the other way around. I'm assuming ordinary uniform convergence here, right? That there's one n that, binds them all, and within epsilon units of, the difference of the outputs, no matter which x, right? That's our usual definition of uniform convergence. And I'm showing you that implies that the max norm is less than that same epsilon. So I'm connecting the uniform convergence, which I've just introduced in terms of this, sequential convergence of this particular max norm versus the garden variety definition of uniform convergence that we already saw. And then, not being content to just do that, I as I say, shall be homework. I want to actually characterize it yet another way, which is to say, if we have a sequence of functions on a subset E of a normed linear space V with norm, if there exists an epsilon n such that the supremum of x and E of this character right here, the norm of fnx minus fx is less than or equal to epsilon n, and that epsilon n goes to 0 as n goes to infinity, then the sequence of functions converges uniformly on E, and we shall call epsilon n a worst case estimator for the sequence fn. It turns out that this is a very nice way to characterize uniform convergence from a calculational perspective. So that is what we're going to do. I think I've almost proved this proposition in the paragraph above, but I'm going to let you guys think about it. Don't go looking for the proof in my other notes. I always punt this off to students. Shane knows. This is funny because we were just talking about uniform convergence in complex like an hour ago. Virtually the same discussion. Anyway, so now the Weierstrass M-test. So if we have a series of non-negative terms which converges, and if you have a subset E of a normed linear space V with norm, and suppose you've got a sequence of functions that have common domain E and take their values in the vector space, and you have that the norm of the functions is bounded by the majorizing term mk for all x and E, then the sum of the series of the functions converges uniformly on E. So what this allows us to do is to gain uniform convergence of a series of functions from the known convergence of a series of numbers. This is very nice, right? Very nice. And the proof is this. So if we have a majorizing series MK, if this is the case, that means that the series of the norm is convergent by the direct comparison test. And furthermore, what's that? Yeah, you know what I'm about to say here. What am I about to say? We can prove the absolute convergence implies convergence in this context. Huh. Oh, that does feel like a homework, doesn't it? Hence, the GK of X is equal. I'm not sure I'll make good on that threat, but it is true. Absolute convergence implies convergence also in this context. So we have that this is a convergent thing, and I'm saying the series, the sum of the series is G of X. So what you have then is that the norm of G of X is less than or equal to the series, the sum of the words, series of the norms, and that of course is bounded above by the majorizing series. All right, so if we look at the tail of the series here, then it's bounded above by the tail of the majorizing series. We can call that epsilon n, but we know that the tail of a convergent series goes to 0. And consequently, this serves as a worst case estimator for that, which shows you then that the series of functions converges uniformly, and so the Weierstrass-M test follows. So I've been needlessly general here. Like, we don't need really all this for this section. I just thought it would be, I might as well state it for a normed linear space, since like the proof for a normed linear space and the proof in the context of continuous functions on AB, it's the same work. Why not get the results for everything rather than just what we're actually working on today? You know. So my apologies. I have grown very abstract for about a half a page, and then I will get straight back to less abstraction here. So if we have a sequence of uniformly convergent functions of continuous functions on AB that converge to a function y, then we can exchange the order of limits. All right? Was this homework? Ah.
This was
This is what we spent all class.
back in the, well, then again, rules and stuff.
Mm-hmm. Yeah, these are, I don't really say what kind of integrals these are, but I suppose it's open to interpretation. I mean, I'm probably Riemann, but but here's the argument anyway. I guess we need a theory of integration which allows the properties of integrals that I'm using. That much is true. So if we have a uniformly convergent sequence of functions on the closed interval AB, that means we have a worst case estimator epsilon n for this. This is, of course, the norm of that yn minus y in there. That has to go to 0 as n goes to infinity. So we can calculate the absolute value of the integral of the difference, right? That, by properties of integration, is less than or equal to the integral of the absolute value, which is essentially what? This is like the continuous triangle inequality, essentially, right? But that's less than or equal to, of course, the maximum of this. That's just, you know, I guess that's like a direct comparison property for integration. I seem like I'm missing a dx right here. Sorry about that, guys. Maybe it is a Lebesgue. I don't have a
I
dx.
was just looking at it to remind myself, it looks like for the Lebesgue dominated convergence theorem, you can do this with pointwise convergence,
Mm-hmm.
but it has to be a Lebesgue interval.
Yeah. It's definitely true for uniformly convergent functions. If it's true in a weaker context than that, I wouldn't be too surprised, but it's at least true for uniformly convergent. I know it doesn't, I know for pointwise convergence, we looked at the counterexamples with in your section as well, right? But anyway, so that's b minus a times epsilon when you do the integral. I seem to be missing a dx. Don't tell my Calc 1 students. Don't worry, I don't have any at the moment. So that goes to 0. And if that goes to 0, that means the limit of the absolute value of something goes to 0 as n goes to infinity, which, because of the way limits work, that implies that the limit as n goes to infinity of the something inside the absolute value must be 0, right? But if that's 0, that forces this to be equal to that, which is what we're trying to prove. So good news. For the Riemann integral, we can also exchange limits and integration, provided we have the Cadillac of convergence, the uniformly convergent series, right? So series of functions. There is also a Banach theorem for operators. This is really, I mean, we proved this already, right? We really proved this already, truth be told. So if we have, let's see here. So, but this context, I have so I'm trying to think, we proved last time, we proved that if we have a normed linear space and we have a contraction map on the normed linear space, then we have a fixed point of that map. And a unique fixed point, in fact, provided, it has to be a contraction on a closed subset. I think really a closed and bounded, technically. I mean, we need to have the, we need to know that a Cauchy sequence inside the set converges to a point inside the set, which you have to make. It's true for if the set is a closed interval, we got it. I think we need a closed and bounded, or if you like, a compact subset of a normed linear space to make it work in the more broad context. So in some sense, this is really just a special case of that theorem we already proved. But I'm going through the proof again here because the proof that's given in Nagel, Saff, and Snyder looks radically different. All right, it looks quite different. So I think it's good for us to see. But here's the context we're going to be working. We're going to look at continuous functions on A to B that are within distance alpha of the constant function y naught. Well, I say a given function y naught. I guess it doesn't have to be constant. But so suppose G is a mapping from S to S, where that's this set. So this is a closed bounded set. And suppose there exists a contraction constant K such that this is true. Then the equation y of y equals to G of y has a unique solution in S. Moreover, the sequence defined by yn plus 1 is G of yn. Well, that's a sequence which converges uniformly to the solution of y equals G of y. Right? And we start the sequence with y sub 0 equals to y sub 0, which seems like I'm saying nothing, but I'm saying something. Okay, so here's the proof. We start out with y naught being a I guess I need to assume it's a continuous function from A to B, right? I think I'm, yeah, okay, great. And then I define yn plus 1 to be G of yn, like that. I say this is reasonable as we suppose G is a mapping from S to S. Right, that's giving us a sequence in S. And since G is a contraction, we can calculate that the difference of yj plus 1 and yj is, well, it's equal to that, right, by definition of the sequence, which then by the contraction condition, we have less than that. I think maybe less than or equal to I'm supposed to put here, my bad, yeah? So less than or equal to, yeah. And then we can keep doing that, right? Keep doing it. And what happens? What we get? Well, let me see if I can turn off half the lights in here. Come on. There we go. So of course, if you keep doing it, and doing it, and doing it, and doing it, eventually you get the power k to the power j times the difference between the first and the 0th iterates, right? So we find that yj plus 1 minus yj, and the norm of that is less than k to the power j times y1 minus y naught. I think, again, it's supposed to be less than or equal to. My apologies. And so following Nagel, Saff, and Snyder, then this is where we depart from the previous lecture, like big time. So check this out. So we rewrite the nth term as this sum. So we add 0 and, like it's a bunch of adding zeros. And so this will simplify back down to yn, right? But you have basically y0 plus the sum of the differences like such. So you can write this. Yn is equal to y0 plus this, this kind of telescoping series, right? So every so often you'll hear somebody say, like, any sequence can be rewritten as a telescoping series. This is why that's true. Because this is a general algebraic identity. You can do this for any sequence if you want. I don't know why you'd want to, but maybe the reason is what we're about to do. But so what this means then is that if the series converges uniformly, then the sequence converges uniformly, because they're the same thing, just with an additive constant, right? So if you just add something, just one term different, like something plus a uniformly convergent sequence is a uniformly convergent sequence, right? So they're not identical, but they're related by just shifting by y0. So uniform convergence of the series gives me uniform convergence of the sequence. And but uniform convergence of a series we can use the Weierstrass test for, which is very nice. So, all right. So the point is that the series is majorized by the geometric series because the difference, the norm of the difference of the, this term in the series is less than or equal to k to the j times y1 minus y0, as we argued before, right? But this is straight up equal to that by the geometric series result we proved last class. And that's less than infinity, right? It's convergent. So this is a convergent majorizing series for our given series. Therefore, this converges uniformly to a function y infinity on s by the Weierstrass M test. I didn't write it here, but, or yeah, I did up here. But by the Weierstrass M test, uniformly convergent. And furthermore, as G is a contraction map, we can say a little bit more here. We can prove uniqueness, all right? So, so if we have, well, I guess not uniqueness. What am I doing here? This is less than or equal to that. Great. Which implies the limit of this is less than that. What are you doing to me? GeForce. I technically have a gaming laptop, but I don't play games. So I believe in the quality of gaming laptops.
Their ability to generate AI images.
That's true. But anyway, I do need to spend more time on my art. But I really need to give some money to something that gives me an uncensored AI image generator. The censoring of Bing is obnoxious. Like you can't just, like you want to make, what if I want Trump to be like riding a zebra on top of a field of candy corn or something, It's going to be like, no, inappropriate content, just because I wrote Trump. It's lame. I digress. So this is the contraction constant, and then if we take the limit of this inequality, we have that, right? But notice that as n goes to infinity, yn does what? It goes to y infinity by definition, right? And I can pass the limit inside the norm here because the norm's continuous, right? So that's 0, which tells me that this is 0, which, again, the limit of the norm of something is 0 if and only if the limit of the something is 0, which shows me that this, without the norms, limits to 0, which means that this is equal to that. But again, this is just that because that's a constant. And on the flip side, this, when I pass the limit inside, well, forget about passing the limit inside. By definition, this is yn plus 1. So the definition is that this is the limit function of the iterate, right? We proved the, so my notation is that y infinity is the limiting function of the iterate. So So what do we have then? We have g of y infinity is equal to y infinity. So indeed, the limit of the sequence of functions is a fixed point for the operator, as we are used to seeing. So y infinity is a fixed point of g. And if we take another fixed point, right, another fixed point z, and if we were to look at the difference, the norm of y infinity minus z, well then that is, because they're fixed points, g of y infinity minus g of z, which is by the contraction property less than or equal to k. I got the less than or equal to now, check it out. Less than or equal to norm of y infinity minus z times k. But the only way that can be true is if the norm of y infinity minus z is equal to 0. So lo and behold, unique fixed point. Right? So aspects of this proof are very reminiscent of what we did last class, but on the flip side of things, like the telescoping thing and the use of the Weierstrass theorem, it's quite different than whatever we did last time, which I've forgotten already. So, so here's the proof. I mean, here's the big theorem. This is the one you should have seen in differential equations, right? But no one in their right mind would prove this in differential equations because differential equations is not a proofs class. And even if it was, goodness gracious, I don't know. Anyway, so suppose f and the partial derivative of f with respect to y are continuous functions on a rectangle, like so, that contains the point x naught, y naught. Then the initial value problem, y prime of x is equal to f of x, y as a function of x, and y of x naught equal to y naught has a unique solution on some interval, x naught minus h to x naught plus h, where h is greater than 0. Moreover, the Picard iteration, I say Picard iterations, recursively defined by, well, start out with y naught, and then yn plus 1 is this, right? Converge uniformly to the solution on that closed interval that we need to construct. We're going to construct this interval on the back of the continuity we're assuming of the differential equations defining function f and its partial derivative. So, and our goal, of course, is to apply Banach's fixed point theorem to the operator t. I guess the t would be like the g in my previous. I've changed g to t now. Anyway, so, and again, I'm following Nagel, Saff, and Snyder, which I'm going to make I'm going to scan chapter 13 and post it for you guys, but I haven't gotten to it yet. So t of y is that, right? Right, great. So we need to show that t is a contraction of a function space S. And we're going to make that function space S like y, that's continuous functions on some interval I that are within alpha units of and this is going to be the constant function y naught, all right? So we need to come up with what's the I and what's the alpha, all right? We haven't figured that out yet. All right. So the argument, as I was just saying, centers on the continuity of the part, the defining function for the differential equation and its partial derivative. And let's see how it goes. So we choose H1 and alpha 1 as follows. To get this rectangle, we're going to call R1. So it's going to be xy such that you're within h1 units of x naught and you're within alpha 1 units of y. And if we do that, that gives us a closed rectangle. So the extreme value theorem then bounds M and L for the continuous functions f and partial y on R1, like so. All right. I can do this because x naught, y naught is a point in the open rectangle, which means there is a closed rectangle around it. So I'm just giving a name to it. I'm, saying you're within h1 units of x naught and you're within alpha 1 units of y naught. We can do this because of the fact that we're in an open rectangle R. We can choose a closed subrectangle centered around the point we're interested in to do that. And more than that, we can bound the continuous function f and the partial derivative by m and l respectively, because again, these are continuous on the closed rectangle R1. And then, and this is motivated in Nagel, Saff, and Snyder, but I'm giving it to you unmotivated. So by magic, we are going to let h be a number that is less than the minimum, and you'll see why as we go on in the proof, of h1, alpha 1 over m, and 1 over l. We need all three of these. And we're going to let I be plus or minus h from x naught, where h is like this, all right? So with this h has three things going for it. It's less than h1, which puts you up in this closed rectangle and makes these estimates hold, right? It's less than alpha 1 over m, which whatever that means. Let's just go on here. So our S is going to be that. We're going to claim that T is a contraction on S so constructed. And we're using the max norm here again. So so we have GI is this is my notation for the max norm with respect to I, okay? Because the max norm needs a domain in order to be meaningful. And we know that exists because, again, we're looking at continuous functions on a closed interval, so the max exists, great. And once more, we're looking at T of G of x is equal to y naught plus the integral from x naught to x of f t comma g of t. These things are all given, so we can define T as such. And as I've explained to you at the start of class, finding a fixed point for T is tantamount to solving the differential equation. So if we can if we can show that, there's a fixed point for T, then that fixed point solves our differential equation. All right. So first up, notice that T of G is continuous. That's just kind of like basic stuff. We're integrating a continuous function of a continuous function, so that's continuous. So the first one's continuous, and then by induction you can see that the nth one is continuous because it's the integral of a continuous function. All right, so induction gives you that. I haven't even typed that out because I'm lazy. So furthermore, for x in that interval that we just defined, we have this minus that. Notice that this minus that is just the integral, right? So up here, subtract that to the other side, you just got the integral. So we've got this integral here. This time g is put in the place of y. And then, let's see here, that's less than or equal to the absolute value of the integral of the absolute value. I'm just putting that there just in case maybe like x naught was before, like maybe the integral, maybe the bounds are like flipped so it's negative or something. So I just keep the absolute value out here to be safe. And then that's less than or equal to m, because remember m bounds this, yeah? So m was the bound for a little f, there it is. And integral from x naught to x of dt, well that one we can do. We get the absolute value of x minus x naught. Now that is less than alpha 1 over m. M's be canceling, and we get alpha 1. So we get this minus that is less than alpha 1, which is nice because that means that if g is an s, then the norm of T of g minus y naught is less than or equal to alpha 1, which is to say that T of g is an s again. So at least the operator T is a mapping of s into s. That's one of the first things we need for it to be contraction mapped, right? So, great. Next we show it's a contraction, and that involves a couple steps. That's where we're going to need the bound on the partial derivative. So, if we have g and w and s and x in the I that we constructed, then this is equal to that, because the y naughts, they cancel, all right? Both of these have a y naught and they cancel, and we're just left with the integral of the difference of the integrals, which is the integral of the difference. So I just go straight to that. And then this right here is the mean value theorem. See, notice that the t is fixed here. So if you apply the mean value theorem to the derivative with respect to y for this function in two variables, we get the partial derivative with respect to y for, for each t, there's some z of t which is between g of t and w of t, such that the partial derivative with respect to y at that particular z of t, it gives us the average change over equal to the instantaneous rate of change, is mvt. And the change is g of t minus. So this is literally mean value theorem applied to the second derivative. And then we bounded the partial derivative of f with respect to y by L. So this becomes that L, and we're left with this character right here. But that, remember, is bounded above by the norm of G minus W. All right? So we have G minus W in the max norm with respect to the interval I, and then and this of course gives us, this integrates to that x minus x naught. But notice that x minus x naught is at most h because x is taken from the interval I, which goes from x naught to x naught plus or minus h. So the furthest you could have x from x naught is h. As such, x minus x naught we can replace with h. And great. So then we say, okay, well, apparently we want our contraction constant to be equal to this. So we're going to make that k. And oh, what do you know? We just so happen to make h such that LH is less than 1 if you go back up. Well, isn't that convenient? Super convenient. Almost like we had that planned ahead of time. Almost like I just copied it out of Nagel, Saff, and Snyder. But so that's where the 1 over L comes into play. Where did it go to?
Top, very top.
Oh, thank you. So if h is less than 1 over L, that means that HL is less than 1. So HL is equal to the contraction constant here. Isn't it? So, wonderful. So we have a contraction mapping on a closed bounded set. And as such, by Banach's, well, anyway, by Banach's fixed point theorem for operators that I showed you a separate proof of today, we have that the sequence defined recursively as such converges uniformly to the solution y for which t of y equals to y on I. Right? I say, well, it still remains to show that any other solution of the initial value problem must reduce to y for x sufficiently close to x naught. And I'm going to let you read Nagel, Saff, and Snyder on that point because I've got more to show you today. I don't want to belabor this. All right. It's not entirely trivial. It's not that complicated either. The arguments are similar to the ones I've shown you. But I'm actually much more interested in the next theorem, which is Picard's existence and uniqueness theorem. Oh, by the way, one of the homework problems that you might face is that last problem, but instead of well, that last problem, but for systems. I think that's a problem we can look at. So, but anyway, here I'm going to state, so here's what's going on. I'm going to state this theorem for systems, and then I'm going to prove it not for systems. Okay, so anyway, so suppose f and partial xi are continuous functions in a rectangle, like such. Now, I think, oh man, I'm sorry guys, my comments are getting jumbled. I'm thinking of the theorem after this theorem. Let me go on. Let's just look at this one here. So we've got this rectangle. T is between A and B, and then we've got, oh man, that was supposed to be an I. Look at that. That's supposed to be Ci is less than or equal to xi less than di for I of 1 to n. My bad. But suppose this contains the point t naught r naught. This is a point in Rn plus 1, right? Then the initial value problem dr dt equals to f of t comma r of t and r of t naught equals r naught has a unique solution in the interval t naught minus h to t naught plus h where h is some positive constant. So the proof goes like this. If we have a vector of real valued functions on the closed interval a to b, we're going to say that set of such functions is Cn AB. And we're going to define the norm of such a vector of functions to be the max of this. And following Nagel, Saff, and Snyder, I'm going to use the Euclidean norm this time. Okay? Like so. Not that I'm really going to ever get into those details, so it's kind of a moot point. Just for the sake of specificity, we're using the Euclidean norm there. And then we could study t of r is equal to r naught plus integral from t naught to t of f of u r of u du. And if we could show that that was a contraction map, then the fixed point of that, through pretty much the arguments I started today with, the fixed point of this operator would then be a solution to this initial value problem right here, right? But now we're talking about a system of differential equations, right? Because R has 1, 2, 3, n component functions, right? So this is a system of differential equations, technically. So once more, the fixed point of the map will serve to give a unique solution to the problem as described in the theorem. I leave the details to the reader. Ah, yes, this is the homework problem. Woohoo! So another thing I might mention here is you might be bothered by the sudden appearance of the Euclidean norm. I mean, why don't I just use the one norm like we did last class, right? So honestly, it's, you know, if I assign the homework, feel free to not use this norm and instead use this one, all right? You may adjust the details if you do this problem, which I will write up in time, but hopefully soon. But anyway, this is really largely a matter of taste because convergence in the Euclidean norm implies convergence in the taxicab norm just the same. So like in the finite dimensional context, if you're in a finite dimensional normed linear space, convergence of a sequence with respect to any choice of norm implies convergence of that sequence with respect to any other choice of norm. This is a special property of finite dimensional normed linear spaces. And as such, you have freedom to choose whichever norm you like. The proof of that is not entirely trivial. If you'd like to see it, I spent about an hour to prove it in the video, which is linked here. Somewhere in here, there's a link. It's in here somewhere. Anyway, it's in this book, Hilbert Spaces with Applications by Loknev, Debnev, and Pyotr Mikazinski. I'm mispronouncing both of those, but anyway, I'm also advertising their book, so they should be happy. So there. Not that it needs advertisement. This is used at like a lot of graduate programs in the analysis program. Sometimes it's used for like a applied analysis class, but. All right, this is the theorem I actually had in mind. That last theorem was just the systems version of the theorem we actually proved in class. So you ought to be able to mimic the proof I gave in class to give the systems proof. But one of the big differences would be, I think that the systems proof is, you can't use the mean value theorem for the systems proof because we don't have a mean value theorem. We have a mean value estimation theorem. So like that is going to have to be modified in that way. But the inequalities, it's not too hard to see what to do. I was halfway through typing it up and then I was like, I'll leave it as a homework. So anyway. You don't have to do all the homework problems, by the way. I'll make sure there's like a bonus one. So if you're not interested in doing that, you can skip it. So this one here, continuation of solution. Suppose you have f partial xi are continuous on the strip. So a strip is this closed interval Cartesian product with Rn, basically. So it's like what it sounds like. It's a strip. It's got containing the point t naught r naught. And suppose that there exists a positive constant L that bounds all of the partial derivatives on the strip. Then the initial value problem, this, has a unique solution, not just close to the point, but on the entire interval. This is a much nicer theorem. I like this one a lot, much more than the last one. I mean, existence of a solution near the point, I mean, it's nice, but existence of the solution on the entire closed interval, that's better. So following Nagel-Saff and Snyder here, I will prove the n equals 1 case, and I'm probably leaving the larger n case as a, well, you know what? Yeah, homework. I still have to say it. Anyway, so suppose you have you're containing this point t naught y naught, and suppose you've got a constant L such that the partial L partial y is less than or equal to L on R. We'll construct t as usual, the integral version of the differential equation. And if y is continuous, then t of y is defined. More than that, t of y is a continuous function, right? Following the induction, you see that we always have a continuous function because we're integrating a continuous function to get a continuous function at the next step, so on and so forth. So we'd like to show uniform convergence of yn on the closed interval a to b. And we can do that by making the same trick we did before. We write yn as this telescoping series, right? So then to capture uniform convergence of this sequence of functions, we can get uniform convergence of that. And we can get uniform convergence of this series of functions if we can apply the Weierstrass M test appropriately. So let's see if we can do that. Well, Now here in this proof, it is literally a strip because we're just looking at the one-dimensional case, right? So it's AB. It's like AB with R. Maybe it's AB with R. I don't know, however you want to. But probably that. You put the, okay, I shut up. So this is a somewhat lengthy argument, though. So here's how it goes. So since this is continuous, right, for t variable and y not fixed, it's continuous. On AB, there exists an M such that we can bound f of t comma y naught for all t in the closed interval. Point number one. Suppose that t is an element of t naught to b. To simplify the argument a bit, that footnote is another threat about a homework. Calculate, because the other half of the argument is to go from a to t naught. So there's a similar but left-handed part of this proof, or whatever you want to say. So y1 minus y naught is t of y naught, like that, which by definition is this. But that is less than or equal to the integral of the absolute value. Great. Which that is bounded by m. So we have this. This guy is less than that. Now, that's point number one. We're going to use that, I think, what follows. Not directly what follows, though, I don't think. So next up, if we have w and v are two continuous functions on this closed interval, then this minus that is equal to, by the mean value theorem, the partial derivative with respect to y, t comma z of t, where z of t is some function between w of t and v of t times the absolute value of the difference of the y parts. All right. Now this is assumed to be less than L, and we have that. All right. Great. Then we'll put 1.5 and 1.6 together in the next step. All right. So we have this. y2 minus y1 is less than or equal to the integral of such. But that is less than or equal to L times that. I think that was the 1.6 at work here, right? We're thinking of this as the W and that as the V, okay? But then this is less than or equal to M times U minus U naught. So here I'm replacing, I had a T in fit 1.5. The T has become a U here. So that's by 1.5. I go from here to here. That's where the M came from. There was an M in 1.5. And then you can pull the M out, it's constant, and you integrate U minus U naught, you get U naught, U minus, that should not be U naught. That should be, that's supposed to be T naught, right? That's a T naught. I'm a dummy. T naught, T naught. Definitely T naught. U minus T naught integrated gives me T minus T naught squared over 2 evaluated. So I get this. All right. And the 2 factorial is suggestive of the fact we're going to keep doing this. So if you suppose inductively that this is less than or equal to that, and we look at this, the same steps I just went through, all right? This is equal to that, then by equation 1.5, I pull the L out, and I take the difference of the second components in the F. But then by the induction hypothesis, this is less than or equal to L to the n minus 1 times M times this integral. Again, that's supposed to be a T naught, my bad. We get this, which is the induction claim for n plus 1. So by proof by mathematical induction, we have proved that the the absolute value of yn plus 1 t minus yn t is less than or equal to this contraption right here. But what is this? Can you recognize what that is? Got an n factorial in the denominator. That's nice.
Power series.
Power series. I like that. What power series of what?
It's like exponential.
It's like exponential. E?
Just about.
What do you think, Jack? Are you going to jump on this, make it a consensus? Math is done by consensus, right? If there's 3, that's a proof almost. It's a quorum. All right, I think we got it.
It's the letter I was
So you guys are right. It is in fact the exponential. It's a little bit off in terms of, so if I take e to the L times t minus t naught minus 1,